Hello, and welcome to my first attempt at a documentary. My name is Tim, and I'd like to talk to you about centripetal force. You may have just noticed that I did not say centrifugal force. That's because it does not exist. I know that at some point, most of you have had explained to you that the outward force you feel, maybe when going around the corner in a car, or on the gravitron at the show, can be related to centrifugal force. But that is not the case, and they are wrong. So then, what is this outward force that you feel, similar to gravity, when going in an orbit, maybe in a gravitron or in a car? And what is the motion of a projectile once it leaves its orbit? These are the questions I want to help explain to you in my documentary. This circle represents the orbit of an object. It may be a hammer on a wire, a satellite orbiting around the Earth, or somebody in a gravitron. There are literally millions of possibilities it could be. Now, this object is accelerating. It may not be changing speed, but it is changing direction. Thus, it is changing velocity, and therefore it must be accelerating. Now, for it to be accelerating, there must be an external force acting upon the object. If the object was to be in space and to be set free from its orbit, where it's in the absence of matter and gravity, it will continue at the same speed, but now it will keep the same velocity. There will be no acceleration. So therefore there must be a force pulling it inwards to continue around this orbit. And there is a force. This is called centripetal force, and it does exist. If centrifugal force was real, and objects were manipulated by it, then that would suggest that when objects leave their orbit, they would do so on the same line as the radius. But is that the case? I've set up 3 demonstrations to prove whether or not centrifugal force does exist. My first one relies on this. My poor representation of one of the greatest siege machines ever built, the Trebuchet. The only 2 major differences I've made to this from the original Trebuchets is its size, of course, and instead of using a sling, I've got a cup, so that way I can better demonstrate the object as it leaves the arm, thus leaves the circular path. For my projectile, I have a little alfoil ball, nothing much. Now, if centrifugal force was real, when this leaves the orbit, one would suggest that it might do so about here, that it would shoot off in that direction. So let's see if that happens. I don't know if you caught that, but it's way over there now. So I have to conclude with this one that does not prove that centrifugal force does exist. Another point. If this was to work under centrifugal force, thereby meaning that the projectile head off in the same direction as the arm, the design would have to have been the other way around simply to get the castle. But moving on to the second demonstration, all I'm going to use is a weight and string. For this demonstration, I'm going to spin it around and try to let go when it's at the top of its arc. Now, if centrifugal force existed, this would head off straight in that direction. I don't believe it will. I'm going to do my best to let go when it's at the top of the arc. I don't know if you saw that, but it went off in that direction. Thereby proving that centrifugal force cannot exist. For my third demonstration, also backing up what I've done with the last 2, all I want to say is, for there to be a centrifugal force on this weight, it would have to be a force exerted from this string. Now, if I was to place this on a table, try to push the weight with this string, it would not work. The string is incapable of pushing this unless it was maybe cemented or used some kind of rock hard glue. It cannot happen. Centrifugal force cannot exist. So that leaves another question. What is the path that the projectile follows? It's an easy one to answer. Inertia. An object will, at any point, continue on its same velocity unless an outside force acts upon it. Newton's first law of motion. So therefore, at any moment, the velocity of the object, that is its inertia, is tangent to its orbit. That is 90 degrees to the radius. The easiest way to picture the action of centripetal force on the object is to think of it happening maybe only once every second as opposed to constant. For this representation, I've got my little drawing of a satellite here, and this is the path of an object. Travelling through space, it has its own constant velocity, but it's attached to a string to the satellite. Once every second, the object is pulled by the string from the satellite, and thereby changing its direction just slightly. So once every second, the object has changed its path, so eventually it's going to continue around a whole circle around the satellite. But unlike this, centripetal force acts constantly. So instead of a jerky diagram like this, it's one perfect fluid circle. Another thing you may now be saying is, well, if these are all directional forces, they must be able to be worked out using vectors. And can they? They can. The most important thing to remember when dealing with vectors, measurement is crucial. For mine, I've used a scale. 1 meter is equivalent to 5 centimeters. Using this formula, average velocity equals 2 pi r over a period. I have, using an average velocity of 20 meters a second and a period of 1, I'm left with a radius 3.1831 meters, or approximately 15.92 centimeters in my scale. And that is what I've drawn here. All these 4 points are 1/10 of a second apart. In my scale, 10 centimeters of distance travelled. The original scale, 2 meters. I've erased the circle between them and just left the vectors there to make it a lot easier to see. But all 3 vectors have been named and linked to the radius. Now, using simple rules of vector addition, you use v2 minus v1, where of course v2 is v2 and v1 negative is the opposite. You're left with this resultant, which also lies along the radius, and this is the velocity of centripetal force. Now, knowing the time span of all this, you can work out the acceleration fairly easily. But there are easier ways to find the acceleration. As long as you know enough information, you can just use the acceleration of centripetal force is the velocity squared over radius, or if you're interested in the force of centripetal force, that equals the mass times the velocity squared over radius. So there you have all the formulas you'll ever need to be able to discover the centripetal force. Well, there you have it. A beginner's look at circular motion by a beginner. I hope now that when you're confronted by somebody in the future who wants to tell you all about the wonders of centrifugal force, you can quite accurately and comfortably tell them how they are wrong, and that all it is a relationship between inertia and centripetal force. I hope too that this was interesting. I know for me, the main high point was finding a legitimate reason to build a trebuchet, and I've learnt a lot about building a documentary. Thank you for your time and keep smiling.